Hi, buddy. This is Mr. Folly, and welcome to podcast 11.2. We're going to talk about energy diagrams with humps, and we're going to talk about my humps. Oh, I have no volume here. This is so disappointing. But an activated complex transition state is unstable, and Hess's law and spontaneity, so let's hop to it. Energy diagrams, exothermic. Whee. So this is potential energy. This is progress of the reaction. So if this is the progress of the reaction going this way, you're going to start with reactants. You're going to end with products. Cha-ching, cha-ching. The activation energy is the energy from the reactants up to the products. So this is the EA. And delta H is the energy change from reactants to the products. Delta H. And the transition state is a physical thing. TS. And there's the activated complex for each. Endothermic. Now, exothermic means it loses energy. So notice, here's the energy of the reactants. Products have less. Heat energy goes out. Endothermic ends up with more energy. So again, PE, progress, reactants, products, activation energy, the energy to overcome that energy barrier. In this case, it's going to be delta H. And then my transition state is still up here. Okay, transition state is also called an activated complex. Speed of the reaction, the size of the humps. Progress. So if you have a big hump, you are slow. If you have little humps, you are fast. And it doesn't matter whether it's endothermic or exothermic, but if I have that, or if I have that, this is still slower. Okay. Activated complex, which is a transition state, is unstable. It's supposed to be that there and that there. It has an illegal Lewis dot structure, so it's not one you would expect to actually work. So it has an illegal Lewis dot structure, so it's going to fall apart quickly. So it's high energy, bad for babies, and bad for transition states. So if you think about something that's being shaken all the time, it's going to fall apart. That's why earthquakes knock down buildings. And that means it will react quickly because it's such high energy. It turns into something else. Spontaneity. I don't know why I put my squirrel picture in again besides just pride. Tells whether or not a reaction will happen, not how fast. So if something is spontaneous, it will happen. It won't tell you how fast it is. It's the opposite of kinetics, right? So water boils spontaneously at 100 degrees, but non-spontaneous at room temperature, which is 20 degrees. Squirrel on the side of the road will spontaneously decay in the winter, and it will spontaneously decay in the summer. It doesn't matter whether it's fast or slow. Equilibrium. Equilibrium, sometimes reactions happen in both directions. So NO plus O2, sometimes NO2 turns into NO plus O2. Smog is reversible. But it is tough to do. You have to change temperature and stuff like that. Precipitation is a reversible reaction. So that means when I have this guy right here, and if I have two particles that have precipitated out, and these are my dissolved ones, what happens is this guy dissolves, and then a new guy precipitates out. Okay. Combustion is not. Why not? Because the gases leave the system. I mean, imagine if it was reversible. Here's a log. A little leaf. See how it's green? And if I let it on fire, fire! Imagine that smoke. Here's my puff of smoke. And it turns into a log again. Okay, if you saw that, that would freak you out. And that would be the first miracle of Pope Francis, the chemistry major. In terms of heat energy, what makes reaction favored? High energy or low energy? Remember, low is always favored. We want to end up as lower energy. It's calmer. It's nicer. It's more stable. It's not going to shake apart. Delta H measures this energy. So is endo or exo favored. So if I have negative delta H, that means exo is favored because I'm losing energy. Potential energy diagram below. Losing energy. Reactants. Products. Notice I'm losing energy. Nature likes that. You can calculate heat using Hess's law. Hess's law is products minus reactants using coefficients. So let's do one of those. I need a calculator. Calculate the enthalpy change in the reaction given below. Oh, I think I have a calculator without a battery. I do. So I'll set it up. So if it's products minus reactants, it's going to be no plus H2O. So I have 4 No. So I'm going to write delta H equals delta H products minus delta H reactants. Every once in a while you see the little sigma sign, which means you sum up the coefficients. My products will be 4 no's, and NO is 90, plus, and then 4 because of the coefficient. 6 waters, negative 286, minus, big bracket thing, reactants, 4 times NH3, negative 46, plus, now they didn't give me oxygen. Now remember, these delta H are the energy to make it, the heat of formation. O2 is an element in its standard state. So all elements in their standard state, and notice oxygen's a gas, in its standard state have a delta H that equals nothing. Okay? So that would be 5 times 0. So then I get out another calculator, I hope. Well, then I'll just do the math and hope for the best. Oh, here's calculator. So then I would do 4 times 90 plus quantity 6 times negative 286. And I'd write negative 1356 minus 4 times negative 46. See all these wonderful negative signs? You're very likely to mess up. So minus negative 184, and we all know minus negative is plus a positive, so negative 1356 plus 184 is negative 1172 kilojoules. Review. Know the parts of collision theory. Know that collisions are common. Know your humps and parts of the humps, which I'm sad you can't hear the sing of my humps right now. Know 3 ways to change rate, and relate those changes to collision theory, and know that this podcast is over.